Welcome to Lecture 7. Okay, I ran a little long in Lecture 6, so I'm going to try to shorten and do a little shorter one in Lecture 7. So the important thing here is that this example is using unbonded tendons, typically associated with post-tension concrete, post-Malone, superior system, all that sort of stuff. But very important for you that you remember that when I tell you you have unbonded tendons, that's a trigger to you to know what FPS equation to use. Don't use the bonded strand, bonded tendon FPS equation. Use this one that we're about to do. Okay, similar beam, similar span. 10 tendons. Again, every single time, every tendon will be 0.153 square inches. So that's just, I know that about as well as I know my own name. There isn't, half-inch diameter strand is 0.153 square inches. It's the only one I have to remember and think about. Also, there is no compression steel in this. Notice I don't have any reinforcement up at the top. That's where the compression side of the beam is. That's where compression reinforcement would be if I had any. Not going to have any this time. There's a reason for that, and you're going to need to know this in later homework assignments. So, 5,000 psi concrete. This is the same section that we had before. Same material properties. But we are unbonded tendons now. So let's calculate at midspan the maximum usable moment capacity, phi mn. Calculate the span to depth ratio. This comes up when we get to multiple spans. A span is defined as the distance between supports. So if I have a 3-span beam, each span has to be looked at independently, theoretically, for this exercise. Every once in a while I get somebody who adds up both span lengths because it's, kind of one beam with 2 spans and does this calculation. That is not correct. Each span, each distance between supports has to be individually considered. So we only have one span in this case, and it's 40 feet. 40 feet divided by 30 inches, 16. It's less than 35. That tells us this is the equation. It's the beam equation. It's the FPS that has 100 in the denominator. That really should always be the case in this class for you. I'm just prepping you for going out and also doing slabs. Two-way slabs are, really the most popular thing. So I don't want to forget that they exist. It's just in a 10-week course, it's tough to get past beams. But if you have beams down, you pretty much have learned just about everything you need to know for slabs. Okay, so this is our equation with these limitations. Rho pre-stressing was the 10 tendons times the 0.153 square inches divided by B, and be careful in this. In fact, your homework and the next example, B is the width of the compression face. So it's important that you identify in this beam. This is a rectangular beam, so you can't get it wrong. But in a T-section, you can get it wrong. And a lot of people will get it wrong. Remember the definition of B. B is the width of the compression face, and this is dP, depth of the pre-stressing, measured from the compression face to the centroid of the pre-stressing. So we come up with a rho value. We remember that FSE is always going to be 174. That's always the case. One-way slabs, two-way slabs, beams, everything in my life, FSE is 174 KSI. So when we go to the FPS equation, remember, now we're talking about failure. This was the everyday condition. This is what this tendon is doing every day of its life. It's not failing every day of its life. Now we want to see what happens at a failure load. So what we're doing is calculating the capacity literally on the brink of failure, and that is compared to the factored loading, which has all the factors of safety in it. It's not the loading we ever actually anticipate, but we've beefed up everything for a major factor of safety, and then we've got to look and make sure it doesn't collapse at that level. That's what ultimate strength, nominal strength, capacity design, LRFD, all those terms mean the same thing. So we plug this in, and the only, I don't even want to say this is difficult, but just getting that row P correct is about all that it takes to get this right, and it's very quick and easy. Nothing like the pre-tensioned people's equation. Come up with 197.8 KSI. The code says FPY is one of the limiting cases. FPY will always be 0.9 times 270. So it's always going to be 243 every time you do that calculation. And every time you do the FSE plus 60,000, you're going to get 234 KSI. So there's not a lot of reason to do that one. You can check it and be anatomically correct with the code, and that's academically correct to check both. But when every single time this calc is 243 and every single time this is 234, the 234 is going to be the controlling case for maximum. Now in this case, our calculated value is less than maximum, so that's the one we're going to use. So, cut the section. Remember, all that's really different in pre-stressed concrete, this is very familiar to you, very easy for you. You had this only in reinforced concrete. Now you have both of these. So your tension force is made up of, your total tension force is made up of two tension forces. The bonded mild steel, and in this case the unbonded pre-stressing steel. Statics tells you that the compression in the concrete must be equal to the sum of the tension. It has to be. So for equilibrium, we know that concrete force is 607.4 kips. What we don't know is where is that compressive force acting. That's why we need this stuff. That's why we need to rewrite this force in terms of 0.85 F prime C A times B. From that, we always calculate A, the depth of the Whitney stress block. That tells us where that force is going to act. We also then need to calculate the neutral axis depth. And that's going to be so that we can check the strain in the reinforcing steel. If we had compression steel, we'd need to check that strain. We need to check the strain in the tension, maximum tension reinforcement, to make sure that it's tension controlled. So that's the reason we need the A and we need the C. So once we do that, we can set up the force diagram. We know where everything is. You can sum moments about any place you feel like. That nominal moment in this case is 1,127.9 foot kips. And I'm assuming, and I'm always going to do that, always going to use that 0.9, put that on there to get the maximum usable capacity. Now I've got to prove to myself that I can use that 0.9, and I've got an example for you. It's very exciting. So I draw the strain diagram. I've got that C value that I calculated, and I calculate that the strain in the furthest tension steel, which is always going to be the bonded rebar, is 0.044. It is less than 0.005, not tension controlled. So at this point, what do? Well, we panic. That's what we do, because we don't know what to do at this point. No, we don't panic. This is what the software programs do. I don't know if you learned this or not. I didn't learn this. Most of the students who have come to me from any of the schools I've taught at don't seem to understand where compression steel comes from. And boys and girls, this is where compression steel comes from. The stork flies by your house and drops the compression steel off in a little basket. Not really. We know that the strain in the steel to be tension controlled needs to be 0.005. So let's set it at that. Just put it there. We always know that the strain and compression in the concrete is assumed to be 0.003. The code tells us that. So we have the strain diagram right there. Now remember, we started the problem without having any compression steel. But compression steel is going to be the answer to the fact that this was not tension controlled. Let's see how it works. So I've set this to be tension controlled, set this to be what the code says. Therefore, I can calculate, even though I don't have compression steel yet, I can calculate what the strain's going to be. By the way, I get a new neutral axis depth based upon this relationship. So I'm calculating the neutral axis depth, the new neutral axis depth, and I calculate that the strain in the steel that I don't have there yet is going to be equal to 0.0021. In this case, that is greater than EY of 0.00207. You may be asking yourself, why am I using that 0.00207? I like having the 07 in there because that's actually the calculation to decide if you have, Fy over E. The debate and the discussion we had before was, what number do we use here? And it's for that number that EY in tension was taken as 0.002. I'm just an old guy. I'm telling you the way I've always done it. This was always 0.005 with no explanation. Whether or not this was yielding or not was checked against Fy over the modulus of elasticity. That number actually is 0.00207. Now the code does tell you can take that as 0.002 and forget the added 07. I never did that. So you're stuck with the way an old man used to do these things. So I don't think for this particular thing that we're doing it's going to change all that much. But that's the yield strain. This is the strain in the fictitious right now compression steel. It is greater. Any way you look at it, it's greater than 0.002 or 0.0207. So it's yielding. Remember, I had calculated that new, what must be the neutral axis if I set this equal to 0.03 and 0.05. So that created a new C. So with that neutral axis depth, A is beta 1 times C, so I know what A is. So now you can see that it's basically, this analysis is telling me what the concrete force is. If A is now a given, because C was a given, and that was all based upon the strain required for tension controlled, I now know what the force in the concrete is under that situation. 0.85 F prime C A times B. So now I've got a force in the concrete. This is the sum of tension. This is the force in the concrete. These sum of compression must equal the sum of tension. Therefore, we can all get out our calculators and add 302.6 plus 304.8 minus 561, and if I've done this right, everybody here will get 46.4 kips. So you know what the force has to be. You know what each one of these forces have to be. Because this is statics, and this is your best friend.
Then come back in, that's my best friend. She a real bad bitch, drive her own car. She don't need no lift.
My hearing's not what it used to be, but she's my best friend. She's got a real bad itch. She's my best friend. There's something like that. I don't entirely understand what that has to do with this song, but the point is statics. Statics is your best friend. So we know all the forces. We know that we have to get that much force into the compression steel, or we have to have compression steel that will take that much force. Now remember, we calculated on that fictitious compression steel what the strain will be because we set up the strain diagram. So we know it's going to yield. Therefore, we needed 46.4 kips, and we've already established with that strain diagram based upon strain or a tension-controlled member that that's going to be 60 KSI. Now here's the question to you. If it turns out that my previous analysis, if I did this and I came up with 0.0018, something less than yield, wouldn't really change much. It's just that instead of using 60 KSI, I would take that 0.0018 and multiply it by 29,000, the modulus of elasticity. You know, maybe in that case I would have 56 KSI or 54 KSI. But I know the strain in that steel, and I know whether it's yielding. And if it's beyond yield, it's 60 KSI. If it's less than yield, it's the modulus of elasticity times that strain. So I know the force I need. I know the stress in that steel, in that strain diagram, and I calculate the area of compression steel that I need. This is the way everybody should be taught about compression steel. This is the way all the software programs do it. And I want you to understand that whenever we come up with the required tension steel for any moment demand, we have no compression steel. We never do that calculation with compression steel being there. It's not there yet. We don't know if we need any. But we provide the area of steel that we need. Remember, the pre-stressing steel was predetermined. That was predetermined by the first part of the course. That was the allowable stresses. So we can't change that. That part's set. When we're going to design, what we will provide is the rebar. That's how we're going to make up the strength that we need. That's how we're going to actually design the section. This is a given. And this is what we can play with to get to what we need, the moment demand, to satisfy the moment demand that we have. But we do that never assuming that we have compression steel. We put the steel in that we need to make everything work, and then we go back and calculate whether or not we have a tension-controlled member. If we don't, which is what this example is all about, this is how you calculate the compression steel required. And that, kids, is where compression steel comes from. So I'm going to make sure that you do this on one of your homework assignments. So we're always, provided that we put that compression steel in, we're always using a phi factor of 0.9. So always, always, always the phi factor is 0.9. There's never any reason to play with the equation in the code. Okay. Very, very important when we have unbonded pre-stressing. Okay, the code, practicing engineers, people who write the code, people who, academics who run tests, nobody likes the idea of there only being unbonded post-tension pre-stressing in a beam. And the reason is that when a beam does crack, Yeah, it's my deflected shape. Well, that's not pretty. Let's see if the other thing in here does that. No, it doesn't. All right, let's go back to where we were. I have to do some editing here. Okay, deflected shape. Cracking. Hey, it worked. So, if we only have unbonded reinforcement, if this beam is to crack, and I told you can never promise anybody it's not going to crack, what happens is you get one large, really large crack. That's ugly, that's what nobody wants, but that tends to happen when you don't have any bonded reinforcement. If you have bonded reinforcement, what you get is a summation of cracks. And they're distributed out and they don't look as bad. In fact, you're hoping that nobody can see them. But that's what bonded reinforcement will do to you, for you. So the idea in post-tension concrete, when you only have unbonded post-tensioning, you must provide some amount of bonded reinforcement. This is not a strength calculation. This doesn't matter if you have all the strength that you need with the post-tensioning only. You absolutely, whether or not you need it, need to provide a minimum amount of bonded reinforcement. So everything can work for strength, but you can still fail the code and get yourself in trouble by not providing the minimum amount of bonded steel. So how do you calculate that? ACT is the area of concrete in tension. It's based on the elastic section properties. And you calculate that and multiply by that by 0.004. You'll come up with the area of steel that you require to be bonded. So now in this particular example, ACT is the, remember, we're back to the elastic section. Don't ask me why. That's what the code says. So we go back to the elastic section properties, not the plastic neutral axis, but the elastic neutral axis, which is, in this case, 15 inches from both the top and the bottom. The bottom of this beam is in tension. So below the neutral axis, add up that area. That is ACT. Pretty easy when it's a rectangle. When it's a T-beam, we're going to see what we have to do there. Not particularly complex, but it's not equal top and bottom. So in this case, 15 inches times the width of the beam is ACT. The minimum area of bonded reinforcement is 0.004 times that, or in this case, 0.96 square inches. In this particular example, we had a lot more than we needed. We have 4 number 10s. That provides 5.08, much more than 0.96. Not always going to be that way, particularly when we get to T-beams. But so that's how the minimum bonded reinforcement is addressed. Okay, one more example. Again, unbonded tendons. That is the big trigger to you about which FPS equation to use. By the way, from this point forward, after you do homework number 4, it's always unbonded tendons. I did a brief homework number 4. I did an example. That was bonded. That was for those of you who are going to ruin your lives and go on to bridge design. Just kidding. Some of my students have gone on to work for T.Y. Lin and some of the bridge companies, and so this is valuable. That's for those of you who may go on that way. And I also just want you to be fully well-rounded pre-stressed concrete people. But we've ended that. That one homework assignment stopped bonded reinforcement. I'm not going to test you on it. Everything going forward, your project, all other assignments are based on unbonded pre-stressing if it matters. So let's do that basically the same example, but let's use a T-beam. Much more realistic for what we're going to do in unbonded, cast in place, post-tensioned, post-Malone concrete. So back to basically the same situation. The 10 tendons, 40 span beam, low point 4 inches, 20 feet away, 4 number 10s. Now we just have a different section. Same material properties we had before. But there are a few points I want to make here. Calculate again the maximum usable moment capacity at midspan. Span to depth ratio, shockingly, with that same 40 feet is exactly the same as we had before. Just want to be thorough. The FPS equation is this for unbonded tendons with this span to depth ratio that has a 100 in it. Be careful. This is where things go wrong. Rho P is now different. This is APS divided by B dP. Be very careful. B is, by definition, the width of the compression face. So we have tension on the bottom of this beam, tension on the bottom. We have compression on the top of this beam, compression up here. So always know, wherever you are, whatever you're doing, where compression is and where tension is. So rho changes dramatically in this case, and that changes that equation substantially. Remember, all we did was change this from a rectangular section to a T-section. That same equation, but now with this number in it, creates a huge FPS. 277.5 KSI. But we can never go past 234. The 60,000 plus the 174,000. So that we cannot use. We're limited to 234. In fact, this should have been a big flag to you that, remember, FPU, the actual failure, was 270 KSI. So we really can't use 277.5. We will have already ruptured that strand. So back to the force diagram. Draw that force diagram. The only difference is we have this huge T-section now. So what changed before, I don't remember what that was, but now it's 234. That 304.8 is the same as it was. C sub C, because statics is our best friend, is 662.8 kips. A, and this will be very typical in T-sections, unless I give you something very strange, and that happens sometimes in your reinforced concrete class just to make a point. But in reality, in any T-section that I've been working with in a normal situation, that A compression block is way up in the flange. As it is in this case, 1.42. So that's what the beauty of the T-section is. We can get that compression force way up at the top. And the larger the moment arm is, the more capacity we're going to have. That only makes sense. So 5,000 PSI concrete, beta 1 is 0.8. So the neutral axis depth is this little tiny 1.78. Let's first calculate strength. And we'll always calculate strength assuming a 0.9 phi factor. Some moments about any point we feel like. 1435.0, a much larger number than it was before if you want to go back. Phi MN, 1,291.5 foot kips. So T-beams are very, very efficient, effective in positive moment bending. So do this for fun. You'll do this once in your life for a T-section. You'll probably never do it again. Set the concrete like we always do to 0.003. This is the neutral axis depth. This strain diagram is drawn, and the strain in the tension steel is 0.043, about 10 times greater than it needs to be tension controlled. That's typical in a T-beam. T-beams are very efficient. They're very ductile. They're terrific, and that's why we use them. So, for your project, if you will remember this, the T-beam in positive bending, which means tension on the bottom, compression on the top, I don't require that you calculate this. You can if you want. It's always going to be on the order of 8 to 10 times more than you need. And like I said, you'll do that calculation once in your life, and then after that you won't do it. So it's okay with me if you make the statement. You can't just not do it, but you have to make the statement that a T-beam in positive bending is always tension controlled. That's good enough for me. Now, this is a major issue. This is where people make mistakes. People don't understand, but it's an absolute code requirement. Irregardless of the fact that you've already calculated that you have the strength for this, there is a minimum bonded reinforcement requirement in the code for unbonded tendons. So minimum bonded reinforcement when you are using unbonded pre-stressing steel, because we don't want the cracks to get extremely wide and very localized. We don't want 1 or 2 very large wide cracks. We want a whole bunch of distributed little cracks if we're going to get them. So that's what this is. It has nothing to do with strength. So in our particular case, the beam was in tension on the bottom of the beam. So the area of concrete in tension, ACT, is 16 inches times that 21.48, that distance right there. Remember, we're using the elastic section for this calculation. That is not the plastic CGC. That's not the plastic C value that you calculated. This is the center of gravity of the concrete section. It's what the code says to do, so that's what we do. In this case, ACT, 343.7 square inches. Minimum amount of steel required, 1.37 square inches. Always remember that 0.004. That applies to beams and one-way slabs. You don't have to remember the one-way slab part yet, unless you feel like it. That's what the code actually says. We have 4 number 10s, 5.08 square inches, much greater than the 1.37 that we calculated we needed. Okay. Now, be careful. I will test you on, and in your homework assignments, I will ask you about this ACT. If you have negative bending where you go over the support, this is the area of concrete in tension. So to understand what the minimum steel at the top of the beam is going to have to be, that's ACT. So you'll calculate that area of steel, or that area of concrete, multiply that by 0.004, and get a minimum area of steel for the top of the beam. Then what we just did was calculate the area of steel on the bottom for positive bending sections, and that will tell us the absolute minimum area of steel that we must have there. We may need more for strength, but we can't provide less than the minimum. So typically we'd start with the minimum and see how well that works. That's what I'm actually going to ask you to do in the project. So in your project, you'll come up with a minimum area of steel on the top of the T-beam that I give you, and a minimum area of steel on the bottom based upon this equation. And that's where we will start. And then you're going to add to it if you need to add to it. Okay, that's the end of Lecture 7. I will see you at Lecture 8.